Anything? All right. My goodness, look at that. That's all messed up. In any case, we are going ahead with diffraction and interference, which are, again, general properties of waves. I keep emphasizing that because I want you to have an appreciation for waves in general, whether it be light waves, sound waves, microwaves, ultrasound that you may use in medical diagnostics. Well, again, you're going to have the same phenomena of if you use an ultrasound, it's a wave of a certain wavelength. It's going to strike some in reflecting surface inside the body. It will reflect somewhat. It will transmit. It will refract. It will diffract around objects. And the same rules and principles that we're talking about here will apply to ultrasound. And so, for example, in designing ultrasound, you have to take into account the wavelength that you're dealing with respect to the object you're trying to image or trying to see. And if the wavelength gets to be roughly the size of the object, then you will get, as you see, when we in this region of physical optics, well, it's just be physical waves. It should be, really. It's more than just optics. It's all waves. When the wavelength is the order of the size of the object, then you start to get these diffraction effects, where the waves will start to bend around the object. And they'll produce these peculiar effects, including interference. As we'll see, the waves will cancel each other in places. So I mentioned interference, namely that you have two waves by some means, and we say that the waves have a phase. Now, I don't know that I defined phase particularly accurately or at all, but the phase of a wave has to do with the fact that you have, we typically deal with sines and cosines. So just let me write sine. It could be cosine, but it's generally that. What you have is a form, typically, that looks like this, 2 pi, which is 360 degrees, x over lambda minus or plus t over the period. You see kind of similarity here. What lambda is the distance in space between two comparable points. T is the period, so this is the wavelength. And let me remind you, it's the length between the crests of any old kind of wave. This could be a sound wave where this is a pressure peak, or it could be a light wave where this is the magnitude of the electric field or the magnitude of the magnetic field, and this is another magnitude of magnetic field. We're not talking about the magnitude of these things. We're talking about the distance. It's a length. It's measured in meters or some other unit of length between the crests of the wave. And the time here, t, is the period of the wave. So it's the time, if you were standing at one place, the time between the time the wave bobs up, bobs down, and bobs up, there's a period of time during which it goes through one cycle at one place. So that's a time in seconds. And, okay. And the other thing that could happen here is that we don't know exactly when this wave will start. That depends on how you start it. So there might be some other constant. Let's call it phi. So the wave doesn't necessarily have to start at x equals 0. it could start, for example, at some other place, and if this is time or space, it could start with some value at t or x equals 0. So that would be taken up by this sort of what we call a phase shift. It's just the constant which tells you where the wave started. In other words, when x and t are 0, what is the value that the wave has? Yes, sir?
Is that pi over 2? Or we could vary from
This phi?
Yeah.
It could be anything. It depends on where you start. It's just saying where's the starting value. Starting value doesn't have to be at 0. It also depends on where you put your t equals 0 in a way. I mean, I could shift my t equals 0. So that's as good of this is the very most general statement. And the phi is just to account for the fact that you don't have to necessarily start at 0. That's sort of starting condition. So let's be clear about that. Now, what phase is this whole bracket here is the phase. It's the angle that the sine is working on. It's the sine of an angle. So this whole deal here is called the phase. And it's an angle. And it cycles between 0 and 2 pi. Because, for example, if you increase the distance from here to here, that's by a distance L, you would add, say, x plus lambda. If your wave advanced, or if you wanted to know the phase at x plus lambda, you just put n lambda in here, and what you'll see is you get 2 pi x plus lambda divided by lambda. See, that's 1. So you get an extra 2 pi. So you get an extra sine of 2 pi. Sine of 2 pi is back to what the original was. You've just gone through one cycle. So the sine of x plus lambda is the sine of this equals the sine of x, which just says that if I go from one peak to another, I'm at the same phase of the wave. If I increase my position by 1 lambda, I'm at the same place on the wave, which is pretty much the definition of lambda. Same is true with the period. If I increase the time by 1 period, you're just adding 2 pi to the sine, and you're back to where you started. So the sine of t plus the 1 period will be equal to the sine of t. You're back to where you started, which just says that if you're at a certain point in time on the wave, if you add 1 period, you'll be back to the same point, and the phase angle will be the same. This sounds harder than it really is, I think. The point that I probably should avoid is to go through the math of this. Namely, it's really trigonometry. That is to say, what we're doing when we're doing these interference effects is we're adding 2 waves. For example, wave 1 might be sine with one particular phase. And another wave, that phi 1 now encompasses the entire x and t and the offset phi 0. All that is in one phase. Then I might have another wave, and I have a second phase that it has. Then when we do interference, what we're doing is adding up A1 plus A2 in some place in space, the same space. and time. So we can, now if we take the case A1 is equal to A2 to make life simple, we can add these, and now I don't remember this from trigonometry because it was a while ago, maybe you do. Cosine, this is just a trig identity, phi 1 minus phi 2 over 2, and sine of phi 1 plus phi 2 over 2. Does anybody remember that? No, I don't think so. That's a while ago, folks. Okay, so that's just the sum of two sine waves. And the point is that the phases could be different, meaning that the angle where you are on the sine wave might be different in the two waves. You might be doing something like that, so that you might be at the this point on one sine wave and that point at the same time in the same space. You might be at a different point on the sine wave. So just to see that that formula works, we could do a couple of special cases. For example, if the two phases were the same, what do you expect to happen? So let's say phi 1 is equal to phi 2. So physically what's happening, we would say that you have one sine wave, and that's your A1, and you have A2, and if the phases are the same, they look like this. And I made the amplitudes the same as much as possible. So you'd have A1 plus A2, and you'd expect sort of more like 2, just adding up. So you'd expect something that maybe looked like that. You know, same wavelength, because I'm adding them point for point. That formula actually gives you the right answer, because it tells you that you get 2A1. Now, cosine of phi 1 minus phi 2, but I say phi 1 is equal to phi 2. So phi 1 minus phi 2 is 0 over 2, so it's still 0. And then I have sine of phi 1 plus phi 2 over 2, but that's, since they're equal, it's 2 phi 1 over 2, or phi 1. So in this case, you get sine of 2A1. Cosine of 0 is 1. And the sine of phi 1. Well, that's what this is. In other words, you get a wave whose amplitude is 2 times this. It's 2A1. And it has the same phase as the original wave. We said that phi 1 and phi 2 are equal. So it has the same phase. I should have perhaps drawn it down here to show that. So that this would be this plus that equals this. This is now 2A1. Everything is in phase, has the same phase, and so on. This you'd very much expect. The other case that's the extreme of this would be that if phi 1 is equal to minus phi 2. Oh, well, no, I don't think I want that. I want a phase difference. Let me make it this way. Phi 1 minus phi 2 is equal to 180 degrees. This would be the case if I have a one-way phi A1 with amplitude A1, and if I have A2, 180 degrees would be this much, right? Between here and here is pi, or 180 degrees. Oh, is this in the way for most of you? Interference. We haven't. Let me go over here then. Yeah, I can do it here, I think. All right. So if the phase difference, phi 1 minus phi 2, is pi, or 180 degrees, the waves would look like, one of them is A1, looks like this, and 180 degrees is this much, because 360 is that. That gets me back to the start. So this is pi, or 180 degrees. So let me put the next wave 180 degrees out of phase, meaning I shift it by 180 degrees. I put it here, and here, and here, and here, like that. So this is a 180 degree phase difference between this and this. Okay? And obviously we'd expect that to give us cancellation, or zero net. So just for fun, we can just run through the formula here. And so the formula says 2a1 cosine of phi 1 minus phi 2. Well, we're taking phi 1 minus phi 2 equal to pi, or 180 degrees, over 2 in the formula. So this is, we're now making this pi over 2, and then sine of phi 1 plus phi 2 over 2. Okay, but the cosine of pi over 2 is the cosine of 90 degrees, which is 0. So this factor here is 0, so that you get the sum of A1 plus A2 is equal to 0, as predicted. So this formula, if you will, is the math behind adding the two waves. Obviously, it gets more complicated if the amplitudes are different. Then you won't get perfect cancellation, you'd expect, because if one guy is bigger and the other guy is smaller, they can't quite cancel each other. And you can get intermediate things between 0 and pi shifts, so you get partial cancellation. But that so that's physically obvious. I don't. You can work out the math, but it's not very enlightening further than that. That's all it is that if they're equal, they can cancel, and if they're out of phase by 180 degrees, they cancel. Okay, so how do we do that? Well, I showed you last time a demo wherein we, this one, the interference of sound waves, where we had a generator which could generate sound waves, or first the generator generates electrical waves. This is the box that generates electrical waves of frequencies in the 1,000 kilocycle range, 1,000 cycle range, kilocycle. Now that electrical signal is sent up to these speakers where the electrical waves cause something to vibrate, maybe magnetically, maybe you create a magnetic field which pulls on a magnet, gets it to vibrate at the same frequency, and hence we create sound by electrically creating a speaker, just like a speaker in your radios or cell phones even. When you hear a person's voice, an electrical signal is being converted to sound, and we get this pressure waves of sound coming out, which we hear. Now, we were able to rotate the speakers, and you could hear that when the path difference between the two speakers to you was a certain place, the sound got quiet because we were doing this kind of thing. Or that, see, when the speakers were equally distant from you, you had two sound waves coming from the speakers to you, equal distances, and you could hear it loudly. If the path difference was about a half wavelength, or 90 degrees out of phase, or 180 degrees out of phase like this, you would get a null, and you would get softer sound. Now that's pretty cool, but it's pretty clear also that you have two sources. Now the interesting thing that happens is you can get a similar effect when you have one source, but you divide the wave into two pieces. So you start out with one source, and let me show you that. That's this demo here. Again, I'm not using light. We will do light, I think next time we'll actually, and you will in your lab next week, deal with light. It's a similar thing. But with here, we're dealing with these microwaves. Turn it on. Let it warm up. And this one. The microwaves, again, have about a 3 centimeter, which is a little over an inch wavelength. And so it tends to be scattered or diffracted mostly by dimensions, the order of its wavelength. Again, that's the same argument that you will invoke when you use ultrasound or anything else. If you have an object which is similar to the wavelength, it will cause the waves to bend around objects. So here's a static source. It's beaming microwaves, radio waves of that wavelength to this. Can you see these sort of slits here? Can you see that at all? People there are in a bad shape, a bad position to see this. But the difference from the sound experiment is that in the sound experiment I had essentially 2 horns, and you were hearing a sound from 2 horns, and they were coming to your ears and interfering on the way, and interfering at your ears when you heard low. Here I have a single source, but I'm breaking it into 2 sources by passing it through these 2 slits. So now I start with 1 wave, and it's coherent, but it is divided here. Now, you would think if things went in a straight line, one beam would go that way and the other would go that way, and there'd be nothing interesting. The fact is, though, that when the wave passes through this slit, it actually spreads out a little bit. This is the Huygens principle acting. When the wave front reaches here, that new wave front sends out little wavelets in all directions, some of which are actually behind this barrier. And likewise with this one, when the wave reaches here, see, I'm interfering here, but blocking. When the wave comes out here, Huygens wavelets come out in this direction, so that wavelets from this edge can interfere with wavelets from this side over here someplace. And so you could get cancellation. And we'll see, let's see if we can see that. Let me turn it up a little bit. So when I'm straight ahead, it's pretty loud. Again, I'm starting with 1 source, making 2 beams out of it, but the beams spread behind the barriers, and I get a minimum here because one of the beams is interfering with the other beam. Now I don't hear too much. Let me turn it up. Actually, if you turn it up loud enough, you can hear a little jiggle. The interference out here is pretty minimal because not much energy has been diffracted in this direction, but I think you can hear it. You hear a whom? Yeah? So there is a maximum and a minimum and a maximum, a whum. And way out here, those 2 beams are interfering, each one coming from a different slit. So I have 1 source, but by dividing it, and they started out the same, but they have different path lengths from that slit to this slit. Oh, there's a big maximum here. Wow. Minimum here. Oh, enough of that. So I think that's pretty demonstrative of what's going on here. We have actually if you want to see this in a little different view, we have this nice applet that the University of Colorado put together, which I will show you here, this guy. Okay. Now, this is sending out, this is very nice. You can vary the frequency of the color of the light. This is supposed to be light. So I can make it bluish. And so the point is, what you're trying to say is that from one source, well, let me do the experiment that we just did, namely two lights. Oh, let's start here. Let's start with one light. It's sending out a spherical wave. If it reaches a barrier, you see that, again, it's pretty much a flat wave coming in, but the amplitude, some wave actually passes back here. And again, we can understand this by Huygens principle, because these parts of the wavefront are sending out little wavelets, and at this corner is also wavelets going out. So a certain amount of energy is actually appearing behind the barrier here, whereas particles would go, you have a nice sharp shadow. Okay, so that's one slit and one source. Okay, now I could make two sources, according to them. Now this would be the experiment we did last week, or last Monday, that is to say, two speakers, and they send out their circular waves, and in some places, along in here, for example, they cancel, and so somebody sitting over here would hear a dull sound, or over here, somebody over here would tend to hear maxima. Again, whatever happens to pass through this slit is spread out a little bit. So let me now simulate let's see. Let me simulate what we just now did, one source and two slits in the barrier. Two slits. Aha. Now, maybe I should start again to make life cleaner here. Sorry. How do I get rid of everything? Reset all. Okay, reset all. Yes, I want to reset. Okay. Let me make it bluish again for some reason. And so here we have one source. That was that klystron sending out microwaves. Actually more in a beam because whatever, but it's close enough. It's kind of flat when it reaches here. Now if I put two slits here, the slit width I can change. But what you see is that in principle, lambda, let me see what happens if I make the slits closer together. Wow. Oh, wait. Oh, that's the slit separation. That's this space here. Okay. But what you see is that, first of all, you get waves diffracted behind the barrier. And maybe I should move this. What you'll see is that there are regions here where there are nulls, and you'll get some energy back behind the screen over here. In other words, you don't just get energy coming forward, as you might expect, but you get radiation going out behind the screens, which is, I think, the experiment that I try to show you. The interesting thing also, and I'm going to demonstrate that also in a moment, is that you can sort of understand this by analogy with the two-speaker thing, because this is, in a sense, one speaker and this is another speaker, and you can understand that when waves from here interfere with waves from here, you can get nulls at certain angles. What's a little less obvious, and I'll demonstrate it in a second, is that if you have one slit, now you would say, well, I have one slit. Where do I get my nulls? It it turns out, you see, that there's waves over here, but there also tends to be a null and another wave peak over here. In other words, what you can get is from a single source, a single slit, it can self-interfere with itself, with the same single slit. And that's because different parts of the slit send out waves, and the different parts can interfere with each other from a single slit. So let me try to, I should have left this on. We can warm it up again. I'll let this guy warm up. And I'll put two of the slits together. And let's see. Well, maybe I'll do it this way. All right, so now I've created just a single slit. It's about a little bit bigger than the wavelength, and I'll try to aim it through the slit. So straight ahead, you get a pretty good amount. You hear it? Now, you hear it coming back? Wah, wah. Way out here, there's a minimum and a maximum. Slight one. Can you hear that? It's whoa, whoa, right there. It's going through. There's a large maximum in the middle. There's an interference minimum, self-produced by this one slit, and then there's another maximum over here. So, in other words, these waves just keep spreading, and they interfere with themselves. And they have this coherence factor because they originally started out. They start out from one source, so they really have the same wavelength, the same frequency, same polarization. They've just been passing through different distances. Even going through one slit to a different place, they've passed through different distances. We can go through the math on that a little bit just to see it in detail. For example, I wonder if I have this on my... I think I have this. Okay. So the point is that what we have here is we get a diffraction effect due to Huygens, and then you get this interference effect because the waves overlap with each other. And so, all right, we can start with the two-slit interference pattern. And let me even, okay, let's start with the two-slit. That's sort of the most obvious, I think. Okay, well, it's really pretty straightforward. You have an obstacle here, and if we just have two openings, and we have just a plane wave coming into these obstacle here, what we want to do is say that this Huygens wavelet is going out in every direction. So let's just take from the middle of the slit to some point up here on a screen. And let's just calculate the extra path length, let's say delta R, that one wave travels compared to the other. Now, if delta R is wavelength over 2, then the phase change, the phase in far as that goes, 2 pi, we had x over lambda was part of the phase angle of the wave. So if you have an extra path length of lambda over 2, up here, you're going to get a sine of 2 pi x over lambda plus 2 pi lambda over 2 over lambda. So you're going to get an extra path length or extra phase angle created of angle pi. And we said an angle, a phase change of pi will give you cancellation. So if we make the delta R equal lambda over 2, then at that angle, the waves from this slit will be out of phase by 180 degrees over here, and you'll get a minimum. So the geometry of the thing is that if you have a spacing, which we call D, the D spacing, this being a right angle, this extra distance here is delta R is equal to D is the hypotenuse times sine theta. And if that is equal to lambda over 2, this will give you a minimum in the interference pattern. So that's basically the equation. Now, in fact, you will get this repeating at several angles. If here is the D spacing of D, you can get not only at where you have delta R 1 lambda over 2. Now, if delta R is 2 lambdas over 2, so here you will get a minimum, or what we call destructive interference. If delta R is equal to 2 lambdas over 2, that will be equal to lambda. So the waves one wave will be delayed by just one wavelength. It'll be back in step. So here, so you're back in step with this one. So this will give you a maximum. But on the other hand, if your phase length difference is 3, or like it's an odd number of wavelengths over 2, then you'll go back to having a minimum, because you'll have one full wavelength plus another half. So what you get is maxima and minima when n lambda is um, 2d sine theta then you'll get, well, no, here we go. Let me get this right for you. What you want is an odd number of half wavelengths, n plus a half lambda lambdas is d sine theta will be a minimum, and n lambdas d sine theta will give you your maximum, where n is a whole number, is an integer. Okay? So if you have an odd number of half wavelengths, you will get minima. And if you get a whole number of wavelengths, you will get maxima. So here's, for example, well, it depends how you want to draw it. But if I draw this wavelength being, the difference being, the path length difference being lambda, I will get another maximum over here. And in between, at n lambda over 2, I'll get a minimum. So, and this n is called the order of the diffraction. So we speak of the first order, which was the first maximum, is the first order maximum, and then you'll get one up here, the second order maximum. Okay? And you repeat like that. So that's the story for two slits, and in fact, it's true, the same line of reasoning leads you to the same formula for many slits. It's the same formula. What happens is all the different slits add up, and you get the same formula. What happens, though, we'll get to the details of that in a moment, but things change a little bit. Now, the less obvious, perhaps, case is but I think it's very, very cute thing here, is if you have a single slit, how do we handle that? Well, we know how to handle two slits, so we just make one slit into more than one slit. This is the way to beat the problem. So you have, say, a single slit, and you say, well, what's the diffraction pattern of that thing going to be? Well, what we can do is we can consider each, we take the slit and divide it in two. So in a sense, we make two slits out of it. And then we consider the light propagating out from just inside the upper part, and the comparable one right here. So that, you see, we can imagine a Huygens wavelet coming out of here and out of here, and going up in this direction here. And if the distance of extra path length, delta r, is a half wavelength, then the wave coming out of this little point will cancel the wave coming out of that point. That's a clever way of handling it. Somebody dreamed this up. I give them credit. And it works out pretty well. So if this were the case, now what we're interested in is not so much the spacing between slits, since there's only one slit. What we have to consider is the width of the slit, which we usually denote by A. So the criterion here is that this extra path length would have to be lambda over 2, a half wavelength path difference, is equal to A over 2. Now that's the hypotenuse of a triangle, and the extra path length is the sine of that angle. So it's A over 2 sine theta, where theta is that angle or this angle. So I think that's very clever. The 2's cancel, and so you get, actually, this would give you a minimum, because those two waves are lambda over 2 out of phase, out of step, and so they cancel. So they can, and the beauty part is, every point, you do the same thing for the next point and its matching point just below. And every one of those points, point by point, has the same path difference. They all cancel. So every point from, let me even maybe with different color, see that one cancels with this one, and then this one cancels with this one, so you get nothing up there because point for point they cancel. That's pretty nice. So, so this is the criterion for the first minimum, that the angle at which the first minimum will occur will be the wavelength over the spacing. That's the angle. And again, what you see is that the important parameter that enters here is the wavelength has to be comparable to the spacing of the material. Similarly to these guys here. Again, the diffraction is important when the wavelength is the same order, because the sine theta can't be bigger than 1. So these are of similar magnitude. In fact, n can't be too big, or lambda can't be too big, because you can't make sine theta bigger than 1. So these things work when the wavelength is of the order of the diffracting object. So there you have, I think, a nice story of a one slit operating is this one, and it produces a pattern where you'll have a broad, I should make it even bigger, like this, front illumination, and you'll hit a minimum, and then as we did with this slit right here, you'll have a secondary maximum here where the waves from the different parts of the slit combine in step and produce you a secondary maximum. So you get this wah-wah effect. It goes wah-wah over here and over here. But these secondary maxima are quite weak, so it was a pretty soft wah-wah. But so you have that effect. That's for a single slit. Now what gets to be a little complicated is that multiple slits, namely the other set, is a combination, really, of a single slit. Single slit produces its pattern, and the multiple slit produces its pattern due to the spacing between slits. And so what you get in a real situation is the product of the two. That gets to be pretty complicated. But what you have is principal maxima due to the fact that you have multiple slits, and then you get a pattern on top of that. Let me perhaps show that. So you have the one slit pattern, which I just showed you. And, well, I'll go into these other things. But you see, what you have is the combination when you have many slits. What you have is the one slit pattern, which is this broad pattern with a little maxima over here, superimposed upon the multi-slit pattern. This is the n, different orders of n. And so your pattern gets to look rather more complicated. You see, you have the broad single slit pattern, and you have the multi-slit pattern that looks like this. So the actual pattern is a product of these two. In other words, this one modulates this to produce this. So if you look in the book, you'll see that they'll show you things like this, that here is the broad single slit pattern, very bright in the middle, dark, light, and on top of that is the multi-slit pattern, these lines here. So this takes a little bit of looking at, but I just wanted to introduce you to the idea that when you see a complicated pattern, I'm sorry, what it is the superposition of all the different things that are diffracting. You have the single slit diffracting in this way, and on top of which you have many of these guys producing a secondary effect, a second effect, which multiply together to give you the total, rather complicated pattern. It's not easy to grab the first time, but if you look at it, I think you'll see that it's not that hard. I just want you to understand that that's what's going on. I don't know that I expect you to really calculate all this. If you not understand the two things separately, you're doing very well. In other words, understand a single slit pattern and understand the multi-slit pattern. The fact that the two, in fact, merge, conflate, adds to the complexity, but it's really just two simple things working together. Okay, we'll pick up on Friday where we'll finish this off. Thank you.